Alright, in this video we're going to start looking at modeling. So we're going to kind of wrap everything up by taking all the function types that we've looked at in this course and look at how they could possibly, describe real-life situations. And so for this lesson, you will need a handheld calculator from the list of approved graphing calculators that you can find on the College Board website. Okay, in my class, that's most commonly a TI-83 or a TI-84. And if you're watching this video because I'm out, I've got, 20 of those on the back table, and, feel free to borrow them, but if you've got your own, please use your own, right? Because that's the one you're going to want to use on the exam, and you want to be the most comfortable with that. So today, we're going to need to be able to use the regression capabilities of a graphing calculator, and that's what I'm going to focus on in this video. Okay, the contextual clues, I'm going to come back and do that in a separate video. But we need to find equations of best fit for linear, quadratic, cubic, quartic, exponential, and logarithmic functions. I'm not totally sure about quartic. I did hear this summer that that was something you needed to be possibly aware of. I think they would probably tell you it was quartic if that was what they wanted. And I'm also not sure about sinusoidal. I think we might need to be able to do sinusoidal regression, but if that's the case, I'll come back and I'll do that in a separate video, right? Hey, now I'm going to tell you the calculator steps last of all. That's I'm going to come back to this front page and we'll write that down, and something that we can easily remember. And as far as regression goes, I think I just want to show it to you on a calculator. In my class this year, a lot of my pre-calculus students are also in AP Stats, so this is something you already know how to do. In Texas, in Algebra 1, this is something that you have to be able to do, so a lot of my students will have seen this before, but if you haven't, it's no big deal. You just need to see the calculator steps, and, if you're working off my notes, or really these are Mr. Passwater's notes, and man, thank you, Mr. Passwater. I don't know you, but I know that you are a fellow, converted AP Calculus teacher. And very willing to share your resources with a teammate of mine, so I really appreciate that. We're going to start by entering the data into the lists. And now in this example, we don't really need to look all that closely at the meaning of the variables in the table, because they're telling us use a linear regression. And so we're going to, like I said, start with the lists. And so we're going over here to the stat menu, okay, all the starts of the stat menu. We're going to edit the lists, and then we're just going to type in our data. 4, 5, 6, 8, and 12. Okay. Then we'll go over here and type in our weight data. Okay, 4.2, 4.4, 4.8, 5.1, and 5.7. Okay, we type all of that in, and then we've got our data in our lists, right? We've got what we're looking for. Now we need to ask it to generate us an equation of best fit, and we want that to be a linear equation. So we're going to stat calculate, because we want to calculate that best fit line, and we're thinking, linear regression ax plus b or a plus bx. Okay, I talked to one of our AP Stat teachers, and she told me, it doesn't really matter which one. I thought I remembered you wanting one versus the other in AP Stats, but I can't really remember. Now, if we're going to need to do anything else with this equation, and you've got this option on your calculator, okay, it would be really nice to store the regression equation in y1. Okay, and if we want to plug in on that equation and predict some other value, or solve for the predicted time at which the baby surpassed 5 kilograms of weight, for instance, we might want to store this equation into y1, and we can get the y's by clicking on the green button and going to F4, because it's in the F4 menu. These are the Y variables. That is not the only way to get there. If you were working with a TI-83, what you would need to do, okay, I'm just going to go ahead and kind of clear that out of there, is you would need to go to the variables menu right there next to clear. Okay, scroll over to Y variables. We're in function mode right now, so we would want to click on function, and that will get me Y1 as well. And that one definitely works if you don't have the newer operating system. Okay, and then we calculate it, and there we've got it. Okay, and on your notes, you can see all those same steps. I just wanted you to see which buttons to press on the calculator. Okay, so here we see a printout of what we need, or what we actually saw on the graphing calculator when I did it. Okay, that didn't go all that well, but y equals a plus bx. Okay, so that's going to be 3.545 plus b is 0.185x. All right, and we can see that r squared and r value. Okay, now that's not really something you need to know for AP Pre-Calculus. Okay, you'll see on the homework video, I'm going to turn on diagnostic and, kind of reason with that a little bit. That's not something you have to be able to do. Basically, the idea of this is the higher R squared is, the better your model is. So something really close to 1 is going to be a really good model, and something not very close to 1 is going to be not a very good model. And 0.9695, that's pretty close to 1, so this linear model is pretty accurate for the weight versus age of this particular baby. Now, as you can see, it's going to ask you a question about this linear model. What is the predicted weight in kilograms of a baby that is 10 weeks old? Okay, and so what we're going to say is, okay, well, the weight, I think they said that was W of t, yeah. Okay, so W of 10 is going to be approximately equal to what we would get if we plugged in 10 into our regression equation. So that would be 3.545 plus 0.185 multiplied by 10. Okay, and we could probably do that arithmetic, right? We could definitely do it by hand if we absolutely had to. We've got a calculator. We just used it. And what that little tip is saying is, if we really want to, we can go out to the main menu and we can just call on y1, which we could get from F4 or by going variables, y variables, function mode, y1, and just plugging in 10, because it's like W of 10 or F of 10. And the calculator's smart, it knows what you mean. And so it would get you 5.395. 5395. That's going to be the approximate value of W of 10. And without the risk of, I don't know, like making a copy error or something like that, we can just plug directly into that equation. Also, in the event that your regression equation has a lot more than 3 decimals, you're going to want the most accurate equation or expression possible. And so you would probably want to store all those decimals, and you want to do that fastest by storing that equation into y1. All right, now I was going to talk about this other baby that's 5.3 kilograms, and so that's where we're going to be interested. Okay, when W of t weight equals 5.3, how old is the baby? Okay, so we might find the value of t that corresponds with that in our model. And in my opinion, the fastest way to do that, especially if we've already got this logged in y1, is just do y2 equals 5.3 and graph and see, okay, I've got this line going here, that's my regression equation, here's 5.3, hopefully we can find that intersection on the standard window. If not, then we'll adjust. Okay, intersection between blue and red looks like it's happening in about 8, I don't know, 9.486, so t is approximately 9.486. And so I would predict the baby was about 9.5 weeks old. All right, now I know I said I was going to come back in a separate video and talk about contextual clues, but it's really not going to take that long, and I think I'm just going to kind of go straight through, especially in the interest of the students in my class that are watching this, because I have to be out. Okay, so while some problems will already tell you, like from the statement of the question, what type of model you need to be using, sometimes you're going to have to figure out what's going to be appropriate. And there's going to be kind of 2 different ways, one looking at the table and one based on contextual clues. Okay, constant rates of change, that's something like with a constant cost or a constant speed, as we'll see in the homework. These are going to be linear models. Quadratic are things that go up and then down, or down and then up, kind of like one maximum or one minimum, or roughly linear rates of change, that's what we'll see on the table, or contexts involving area. I really want to emphasize that. And then cubic models are oftentimes good for contexts involving volume. And we could also see that a cubic model would be good in a situation where we had a table with evenly spaced x's and constant third order differences, or nearly constant third order differences. Okay, so for each of these situations, we're going to determine whether it's linear, quadratic, or cubic to be best. And these, I will say, are also on the homework, but, really, I think these are a good set of 3 that will be important for us. Okay, balloons are filled with water in preparation for a water balloon battle. Okay, radius of the water balloon is measured relative to the amount of water it holds. Okay, amount of water, that is volume. I'm going to just do the exact same thing I did on the homework. I'm going to say, all right, we've got volume here. And we just said, for volume context, we need to be thinking about cubic polynomials. Okay? That's just one of the essential knowledges from AP Pre-Cal, is if you see something that's trying to model a volume, your first thought should be degree 3, because volume is a 3-dimensional measure. Okay, now we've got Totino's pizzas on sale at the local grocery store. Okay, the price of one pizza is between $1.99 and $2.19, depending on just like what I guess the toppings are. And then think about the total number of pizzas relative to the total price of those pizzas, right? And we don't know like how many of each variety were bought. We know they're approximately $2 each, and we have that each thing. That's oftentimes that's going to be a linear type situation. So that each or that constant rate of change, that's going to give us the linear. And it's not an every time thing, depending on variety. They didn't actually even use that word. But and then in the third one, it's talking about a sprinkler placed in the yard, rotating in a circular pattern. The radius of the circular path is measured relative to the area. Okay, as soon as we see that area word, we need to be thinking quadratic. Okay, so area is going to be quadratic. Okay, and that's kind of like as far as we're going to go with contextual clues, at least for now. All right, now we've got another example, and I really like this one because I think it's kind of got a few different thought processes I want you to go through. So table is going to give us data for 8 ordered pairs. It's going to ask us which function type best models the data in the table, linear, quadratic, or cubic. And so it's like, okay, well, if I got a table, maybe I should think about first, second, third differences. But I look at the x's, and they are not evenly spaced. I've got 0.4, 0.5, 0.3, 0.5, 0.5, 0.7. Okay, that's a little too far off, right? So that can't be the thing to do. Look, they're looking at third order rates of change. That's probably not it. So I need to think more generally. What are the y coordinates doing? They're going from 5 up to 18, then back down to 2, up then down. That's going to be quadratic. And I'm just going to say quadratic, and the reason I would give is that y first increases and then it decreases. So that's kind of like the shape I'm looking for. And so I'm going to think about a quadratic model and possibly run a quadratic regression. Okay, so I've got my calculator. I'm going to type the data into the list. But first, I'm going to show you if you're like a statistician or you're the type of person that wants to turn those diagnostics on so you can see that R-squared value and think about the quality of your, regressions. You can go over here to catalog and D and then scroll down to diagnostic on, press enter, run that command, and then it'll give you the R-squared, at least until you clear the RAM. Okay, but now I'm going to go to the lists, which I could do by pressing stat and then edit. I'm going to clear out those lists, and I should probably show you this. I go to L2, I press clear, and then down, and then it clears it all out. And I can go do the same thing for list 1, clear, and then down. Yeah, there we go. And I don't have to press delete for each entry. I'm going to type in all of my data, and then I'll be ready to run a regression. So I'm going to go to stat, calculate a quadratic regression. See, that's right here, quadratic regression. That's option 5. I'm going to ask for that. Okay, X list, list 1, Y list, list 2. That's what we want. We don't want frequency list because we're not in a stat class. Oh no. I don't know what's going on there. Oh goodness. I think okay. I don't know what right click did, but that was obviously not what I wanted. I want to store this into Y1 because we might need to do something else with this in the future. And I'm going to calculate and get that, and look at that, R-squared is 0.99999. This is obviously a very good model, very, very close to a quadratic relationship between x and y. So I'm going to copy in my result, and there I've got myself a quadratic polynomial that models the data really, really well. Okay, and if we wanted to, we could go look at the stat plot and see that, and maybe I should show you how to do that. So if we wanted to see this one, and again, I don't think this is something you need to be able to do for AP Pre-Cal, but I'm not totally certain. You go over to stat plot second, right there. We're going to, stat plots are off. I'm going to go to plot 1. I'm going to just turn it on, and then I'm going to go to zoom to stat right there, zoom 9. And I'm going to, ask it just to graph that, and oh look, there are my data points, and there's my regression equation going right through them. So this is a really good equation. The next section of the note starts talking about this competing function model validation. And this, I think, fits right in with what we were talking about before, like which model do I choose? That's a valid question that we need to tackle in this course. And so there's going to be a lot of linear, quadratic, and exponential, and so that's what we're going to mainly be focused on, but we do also need to be concerned with logs, which I will show you in this video, and also, cubic and possibly quartic and maybe even sinusoidal as well. Again, I'm not sure about that. We'll address that in future videos. Okay, so we need to determine which is most appropriate given a set of data or contextual clues. We just talked about that. Let's move forward and talk about the actual data itself. So for linear, we need to be seeing a roughly constant rate of change or constant first order difference when the x's are evenly spaced. Okay, and so that's the first thing I'm going to look at this data table and be like, hey, I'm noticing these x's are evenly spaced. And so I'm going to think about the difference in y values for those evenly spaced x's. From 1 to 2.6, I increase by 1.6, then I increase by 2.4, then I increase by 1.4, and then I increase by 2.3. And, these are all, kind of near 2, between 1 and 3. And so this is approximately, roughly constant rate of change. I don't love that, but, it's not like it's, the rate of change is clearly increasing or clearly decreasing, right? It's about the same. Okay. The next one is quadratic, and we can definitely see based on the graph, like if they plot the points, we can see that, but what if we're only given a data table? We look at these x's, we see once again 0, 2, 4, 6, and 8. These are evenly spaced x's. So let's look at the, first order, second order differences. So 9 to 3.95, I believe that's a decrease of 5.05. And then, if I keep, doing this is a little bit tougher. I had to do the arithmetic, ahead of time. We'll get these. And if we look at the second order differences, we'll see that they're, going from -5 to -1.85, which is about -2. That's an increase of about 3. Okay, this would be an increase of about 4, going from about -2 to about +2. And then from 2.1 to 4.6, that would be, about increase of 2.5 or so. So we're seeing a roughly constant second differences, and so that would give us evidence we were looking at a quadratic relationship. Okay, I think the more telling pattern is that, y decreased and then increased, and that's all we could see on the table. And I think that's going to be like the most common thing for us in AP Pre-Cal to look at the table, more so than looking at the second order differences. It's like, oh, it decreased and then it increased, or it increased and then it decreased. The most simple explanation for that would be a quadratic relationship. Now, with exponential, that's what we're going to be seeing increase at an increasing rate of change, right? So if we did the rates of change, we would see, that the rate of change was increasing each time. But if you go 0.5 to 1 to 1.9 to 4.2 to 8, it's like, oh, that's a half to 1 to 2 to 4 to 8. And for evenly spaced x's. And so it's kind of like each time multiplying by 2. And that would be an exponential type pattern. Now, of course, I don't love this. If you know me, that I would like for it to be, exactly an exponential relationship, but that's the whole modeling thing, is that sometimes you get these actual data sets and they're not perfect. And so that level of creativity, I worry about that for my students, but I think if I just show you that that's something that you have to be aware of, and you've seen it before, then that's something you might could recognize in a test situation. Right, so this example is saying just plot these, make a scatter plot and plot the points and think about what kind of relationship would be best based on the shape. So, okay, 0, 11, plot the point. 2 and 8.2, this is something that we're good at. 4 and 5, 6 and 2.3, and then 8 and -1, which goes a little bit off the grid. Okay, I see the pattern. This looks like a linear relationship. So I'm just going to say right here, linear, and move on. Okay, we could look at the first order differences relative to the change in x, but I don't think that's necessarily what we need. Okay, for B, I'm going to plot each of the points carefully, right? But it doesn't even actually matter that much how careful we are, especially with these decimals, because we're just supposed to see the pattern here. Okay, I increased and then decreased. Now the shape of this thing's a little bit off, honestly, but I don't think piecewise linear is kind of in our playbook yet. I know that's going to come up on the homework, and I guess I'll talk about that at the end. But yeah, I think that's just going to be up then down. That's got to be quadratic. So I'm just going to say quadratic and move on. All right, now Part C, okay, I was kind of wondering if this was going to happen. If we plot the point 1 and 10, 3 and 5.2, 5 and 2.4, 7 and 1.3, and 9 and 0.7, we see that it's decreasing, but this is definitely curved. Linear is not going to be a good model for this thing. I'm really seeing, pretty much like, let's see if it, how it likes that. I'm seeing something like that, and that looks like exponential decay. Okay, so based on that and going back and looking at this, 10 to 5 to 2.5 to 1.3 to 0.7, it's dividing by 2 every time, okay, and the x's are evenly spaced. So I think this one's going to be exponential. And so I think definitely with the scatter plot as, a clue, we could go back and look at the table and be like, yeah, it does look like it's dividing in half every time. And I think, especially in like a multiple choice scenario, maybe the answer choices would give you those clues. Okay, and this next one's kind of the same thing. I just plotted the points for you. You don't need to see me plot points. I'm seeing that it's increasing, but the rate of change sure seems to be increasing as well. I do have evenly spaced x's, so I'm going to go and think about that. I've got plus 1, plus 1.5, plus 2.25, and then plus, I think that would be 3.5. And it's like, okay, this rate of change is definitely increasing. I'm not sure if it's, 1 to 1.5 is an increase of a half, then 3/4, then what would that be? 3/4 again? I don't know. I'm not really seeing it, but now if I look over here, 2 to 3 is like multiplying by 1.5, 3 to 4.5, again multiplying by 1.5, 4.5 to 675. Yeah, I'm adding 2.25. This is a perfect exponential relationship, and this one's a little bit tricky. But I see the curvature through here, and that's going to give me pause. Obviously, that curve I just drew didn't quite snap to a perfect exponential, but I'm going to again say this one looks exponential to me. All right, now I am realizing that these notes are not going to ask you to write a regression equation for an exponential, and that's something we need to be able to do. So I'm going to do that right now with this one over here that's not quite perfect. So I'm going to say get a regression equation. So we're going to go to the stat menu, edit the lists, enter my data, go to stat calculate, just like I did with the linear regression or like I would do with a quadratic regression. And I'm going to, you could scroll down or you could scroll up to see exponential regression. That's going to be option 0 for me. If I wanted to store the regression equation in y1 because I knew I was going to need to use it again, I could, but I'm not going to. So I'm just going to say, all right, y equals a times b to the x. So y equals a, which is 13.773. Remember, always 3 decimals in AP Precalculus. So times b to the x, 0.715 to the x. And there I've got myself a regression equation in an exponential context. All right, so now I want to talk to you about modeling with log functions. And the kind of motivating example is this average salary versus church size for like a church pastor. And I think this is actually pretty interesting. It's pretty clearly seeing that the salary is going to increase as the size of the church increases, which makes sense. But with limiting gains, right, at a certain point, like the more members you add, it's not like you're getting a certain dollar amount per member. And so we're seeing we are increasing salary at a decreasing rate. And, you can see that thing in the box for a given set of data. If the input values appear to change proportionally, when output values increase, what did I say, when output values are evenly spaced, then that's a logarithmic relationship. I think to us, the more telling giveaway is going to be that the function's increasing at a decreasing rate. I think that's going to be the most common situation for us. So in this first example here, selected values of the logarithmic function L are given in the table above, where L is a plus b log x. This is only 2 data points, but this will be enough because there's 2 unknowns, a and b, right? So we're going to use the given data to write 2 equations that can be used to find the values for constants a and b in the expression for L of x. Okay, well, we have 2 facts that we know. L of 2 equals 3, and we also know that L of 5 equals 7. Okay, we could probably find the exact values of these if we wanted to by hand, but this is going to be a calculator type situation, and so we're going to use the calculator for it. So L of 2 equals 3. What is that telling me? Well, just plug that in. L of x, that's 3, equals a plus b times the natural log of x, which was 2. Okay, well, that's an equation. And then a second equation is L of 5 equals 7. So 7 would be what I get when I plug in x equals 5. A plus b natural log of 5. And these are two equations that we could use to, we could set a equal to we could solve for a and set the two things equal to each other and then solve for b. It would be kind of annoying. We solved log and exponential equations a long time ago in this class, but now we've got technology. Let's use it. I'm going to get out the calculator, go to the stat menu, edit the lists, clear out the data from last time, type in our new data, then go ahead and run a log regression. So we're going to stat calculate a log equation that will fit this data. So that would be 9 natural log regression. Okay, I don't think we're going to need to be doing anything further with this equation besides just finding the values of a and b. There we go, a plus b log x, b natural log x, whatever you want to call it. So I would say a equals negative 0.026 and b would equal 4.365. And that's, in the simplest case, how we run a log regression. Now back to the church size versus average salary example, they're going to give us the actual data from the previous page. So we're going to use the regression capabilities of our graphing calculator to find a logarithmic function model for the data above in the form a plus b log p, where p represents the church size and s is the average pastor salary in thousands of dollars. And then we're going to use that model, so we're going to want to store that regression equation. And in the event that you have a TI-83, I want to show you how to do that as well. I think I neglected to do that in the other situation. Okay, but first I'm going to need to enter my data. So I'm going to go to the stat menu. I'm going to ask to edit the lists, and I'm going to look. Oh, look, they're already in there. I already put them in there. So I've got all those data points in there, and you do want to double check, especially when you've got a long data set. You should definitely double check all of your values to make sure that they're right, because if one of them's wrong, you're going to end up with the wrong answer, and there's not really anything you can do about it, right? So it's worth a second check. I definitely checked the output values a second time, but 300, I'm going to do a random check, 300, 450, 650, 900. Okay, yeah, I'm just going to hope for the best on that. Really hope I didn't type in anything wrong after I just talked about, there's no hope for you if you type in something wrong. So we're going to ask for a log regression, calculate, that's option 9. I am going to store this equation into y1. Now, I've already talked about if you're using an 83, you go into variables, y variables to call for y1, but then you calculate, and see that's the command right there, and I think that might be what you have to do, and I will show you how to replicate that if you don't have the nice menu. I can't remember how it works on a TI-83. Let's copy my equation first. But I'll say, okay, if I was going to be doing that on 83 and I had to type it in, I need natural log regression, and then the syntax is like list 1 for X list, list 2 for Y list, and then Y1 for storing it, where the comma is right here. If you need to get at those lists, they're right here in blue, so it would be like second and 1. And I don't know if that's going to be anybody in my class or anybody watching this video, but if so, I just want to make sure you're aware that that's the syntax, that's how you do it. You give that command to get the exact same results. Okay, so using the model found in part A, what's the predicted annual salary in thousands of dollars for a pastor whose church size is 500 people, and that is actually like the value of P. So I'm going to just plug in P into my model. I'm going to call for Y1, which I could do from F4, or I could do from Y variables right here. I'm going to plug in 500, and I'm going to have it do the work for me, and that would be 94.329 or 330,000. Okay, so salary would be 94.330,000. Okay, and I think that's going to be all for this, for log regressions. Okay, I got one more thing to tell you about. Really, the last thing I want to tell you about is this one thing that comes up on the homework that I'm not even sure if we need for AP Pre-Cal, but I just want to talk about distance from home on a very oversimplified trip. So suppose I leave my house in the car and I am just driving in the neighborhood and I'm going at 30 miles per hour. My distance from home would be increasing constantly, at that rate. And then suppose after that I got on the highway and my speed increased and I was able to go 60 miles an hour. Okay, my distance from home would be increasing faster and the graph would get steeper. And so this is a situation we would describe as piecewise linear, but I'm really not sure if or how that could come up in AP Pre-Cal, so I just want to throw that out there because it's on the homework. That's all for this video. Thanks for watching.